On Friday about the ideals and the class group, tell you a little bit of how the theory developed after it was discovered. And then we're going to meet again for various review sessions in January. We haven't fixed the time and place yet. We'll let you all come back. It won't start before Monday, January 5th, that I promise. At least I think that's a Monday. And we'll get in a couple of review sessions before the exam so everyone's ready. I realize it's very awkward in a course like this to prepare yourself and learn all this material and then take a whole month off and then try to remember it. And maybe if we change the calendar, we'll be able to do something about that. We'll see. That's part of the curricular review. Okay, so let's say where we were. We had these rings associated to a discriminant, and I'm going to take the discriminants to be less than 0. So the uniform way of writing these rings is it's z plus z, d plus root d over 2. And this was a subring of the complex numbers. And when you put the elements, when you describe the elements of this ring inside the complex numbers, they formed a lattice. And we started to look at the ideal theory of these rings. So the first thing we observed was that if you had an ideal which was not equal to 0 in this ring, that it had finite index, and I'm going to need a name for that index pretty soon. So you could call that index RD modulo I, but I'm going to call it the norm of I. I'll say why in a second. And the reason is that if you take a principal ideal, if I is equal to alpha times RD, then you find that the norm of I is the same as the norm of alpha. The index of this ideal we showed was, remember, the norm of the element. This is the norm of alpha is alpha times alpha bar. So for a general ideal, whether or not it's principal, it does still have a finite index, so we can associate to it an integer which is bigger than or equal to 1, called the norm of the ideal. Okay, now, if you want to get far in the ideal theory, we want to sort of measure how far R of D is from being a principal ideal domain. Far away from a principal ideal domain. Well, you have to make that precise, but there are many cases we've seen already where not every ideal is principal. But can we make a measurement about how far they are away from being principal? So the idea in this was introduced in the mid-19th century, and first of all, people generalized the notion of an ideal a bit. So they generalized the ideal to what's called a fractional ideal. Peter, did you do fractional ideals last time? Okay, I'll do fractional ideals, but this is similar to what Peter did to get to a notion of a group. A fractional ideal is a generalization of an ideal. It's an I, which is a lattice in C, stable under multiplication by R, and the only difference is it's not necessarily contained in R. It's contained in the quotient field of R. It's contained in Q square root of D. But not necessarily contained in the ring. So I'll give you an example of a fractional ideal, perfectly reasonable example of a fractional ideal. It can't be the whole field because that wouldn't be a lattice. It has to still be this discrete subgroup. Under addition. So this is an ideal. It has to be a subgroup. So it's a discrete subgroup under addition. and you can multiply by elements in the ring and you stay in this. So an example of a fractional ideal that isn't an ideal is you take an element beta, which is in the field, which is non-zero, but might not be in the ring. And then you consider the ideal I, which is all multiples of r by beta. Like you might take 1/2 of, multiply everything in r by a half. So for example, if r were the Gaussian integers, so here's the ring R of Gaussian integers, we might have the fractional ideal I, which is this is z of I. We might have the ideal 1/2 times r, which would be the things here. And that's still a lattice. It's just not contained in R. Okay? So you can get slightly larger things than R, which still have the property that they're stable under multiplication by R, but they're still not everything. They're still a lattice. Those are called fractional ideals. And just as we had multiplication of ideals, generalizes to multiplication, and we're going to see right away why we wanted to go to fractional ideals, of fractional ideals. Namely, if I have two fractional ideals, I define the product I times j as the collection of all sums alpha I, beta I equal 1 to n, such that alpha I is in the fractional ideal I and beta I is in the fractional ideal j. So it's the natural fractional ideal you'd get by taking all the products, which you'd have to have, and then taking all sums of those things, because it's got to be stable under addition, and then that's closed under multiplication by r. So this is a very complicated idea of multiplying ideals, and you probably did this for your homework and you did it on Friday. It's not a priori clear when you multiply two ideals what ideal you get. However, there is one really simple case. By the way, this ideal, if you multiply two principal ideals, if you multiply alpha r times beta r, that's the only case where it's simple. And the answer is you get the principal ideal generated by alpha beta. It's the only simple case. And the reason is that everything in here is of the form alpha times r, and everything in here is of the form beta times r prime. And if you multiply something here times something here, it's of the form alpha beta r prime, and taking sums doesn't change that. So you get another fractional ideal of this form. So multiplying this ideal by a principal ideal, so if I wanted to multiply this by the ideal, if j were the ideal, say, generated by 2 plus I, that's an ideal of norm 5. If I multiplied I times j, I'd get the ideal generated by 1 plus I over 2 r. So principal ideals, it's easy to multiply, but general ideals or general fractional ideals, very mysterious. Okay. Now the big result, which Peter probably talked in a slightly different way about last time, is the following. Proposition. And this was proved at the end of the 19th century by a number of mathematicians, Kummer, Dedekind, is that the fractional ideals form a group under multiplication. That's the first statement. 1. So what is the content of that? Well, it's pretty clear that this is a commutative operation. I times j is the same as j times I. It's also clear, since multiplication is associative, it's an associative operation. So what you have to be able to do to prove a result like that is to figure out what's the identity object And what's the inverse object? Now the identity object is pretty clear. Can someone tell me which fractional ideal under this crazy kind of multiplication will take a fractional ideal into itself? R. Good. With identity, the ideal R, yeah, which is generated by 1. If you multiply any ideal by R, if you just look at this, you're just summing up the elements in that ideal times elements in R, which are just elements in that ideal. So that's pretty clear, that I times R is equal to R times I, which is equal to I. That's easy. What's hard is to prove that there's an inverse ideal. That's the content of this theorem. Content is existence of inverse such that I times a new ideal, maybe I inverse, is the ideal R. That's not clear at all. It is clear for principal ideals. What would be an inverse to the principal ideal alpha times R? Yeah, exactly. Alpha is a non-zero number. So in the field, you can write 1 over alpha, right? And 1 over alpha still gives a fractional ideal, which is why we needed fractional ideals, to be able to invert things. So if alpha is in R minus 0, 1 over alpha is in the field, square root of d, but perhaps is not in R. On the other hand, if you multiply the principal ideal alpha R, the only possibility for its inverse is 1 over alpha R, which is R. And that's why we had to introduce fractional ideals. To even invert principal ideals, we'd have to introduce these. Yeah?
Does proposition hold in arbitrary algebraic fields or just in imaginary factors?
No. It's a proposition that Dedekind proved holds in arbitrary finite extension fields of the rational numbers, where one has to work with the proper ring inside of there. Namely, this was the ring of all algebraic integers. If you do that, it works. If you don't, even if you were so stupid as to work with a ring like this, you see, we saw that one of our rings is this, 1 plus the square root of minus 3 over 2. Now that contains, with index 2, the ring z plus z squared of minus 3. You know, I just realized if I use this board, oh, never mind. Okay, here the theorem is true. Here the theorem is false, which is another reason why we had to introduce all algebraic integers. So that was a big observation of Dedekind, that you had to be in the biggest ring to get this thing to work. Okay? So, all right, so the key thing is the existence of the inverse, which I'm not going to do. The second proposition is the principal ideals form a subgroup. Well, that's clear, right? If you multiply two principal ideals, you get another principal ideal. The identity is a principal ideal generated by 1, and the inverse of a principal ideal is a principal fractional ideal. Okay? So you have the fractional ideals form a group under multiplication. The principal ideals form a subgroup. Now, if every ideal were principal, then this subgroup would be the entire group. If every ideal is not principal, then there's some things in the group that aren't in the subgroup. So it suggests that we should look at the quotient group. Right? That would measure the fact how far we are away from being a principal ideal domain. It's a concrete measure. All right? And that's the third section. The quotient group, which I'll call CD, because it depends on this discriminant D, is a finite group, which is called the ideal class group. So Peter defined that last time without going to fractional ideals by putting an equivalence relation on the monoid of all ideals. But it's a little classier, at least from our point of view, because we know about groups and subgroups and quotient groups, to first define an abelian group. This is, of course, an abelian group. Now, this group is infinite. If you take any prime ideal and just take its powers, you get an infinite number of ideals. So this is an infinite abelian group. This subgroup is also infinite, but the miracle is when you go to the quotient group, it's finite. So things are close to being a principal ideal domain. There are rings, by the way, where you have this is true, you have this is true, and then the quotient group is infinite. So this is a nice statement about these rings, that the quotient group is finite, they're close. And once you have this theorem, and people were very excited to find this theorem, you have a measure of how far away you are from being a principal ideal domain. And that measure is, in some sense, the order of this quotient group, the class group. And they gave that a name. So we let H sub D be the order of the ideal class group C sub D. And once Dedekind and Kummer had identified this group and identified its order as a very important invariant of this ring, it became an interesting question to compute it, right? And to tabulate it, because if we could find examples where the class group was non-trivial, those are examples of non-principal ideal domains. So here's a table. I'll give you the first couple of discriminants. So -3, -4, -7, -8, -11, -15, -19, -20, -23. So we've tabulated these discriminants before. And then I'll put next to them what is the class number. So here the class number is 1. Here the class number is 1. Here the class number is 1. Here's the class number is 1. This looks very bad. The class number is always 1. It's always a principal ideal domain. But when you get to 15, the class number is 2. 19, it's 1. 20, it's 2. 23, the class number is 3. And people made Gauss, and because he was thinking in slightly different terms, but Gauss and Dirichlet made elaborate tables of these class numbers. And they found that the class numbers appeared to be growing. And in fact, the last time HD is equal to 1 is D equal -163. They didn't find any other principal ideal domains. There were only finitely many of the rings on this list that were principal ideal domains. And in fact, it appeared that HD was growing as the absolute value of D was growing. And Gauss guessed that the size of HD was approximately the square root of D. So as a function of the discriminant, these rings were getting more and more and more complicated. If you had a discriminant which was 10 to the 100th power, had 100 digits in it, you would expect a class number that had 50 digits in it. Still a finite number, but large. And Gauss had a lot of experimental evidence for this, but couldn't prove it. And it became known as the Gauss's class number problem. Okay, now, in fact, the correct estimates, this is kind of vague because it doesn't tell you. I mean, if it were more precisely, what Gauss conjectured is that the class number with respect to D is less than some constant times D to the 1/2 times the log of the absolute value of D, and is greater than some other constant, C prime, times D to the 1/2 divided by the log of the absolute value of D. So basically is the same order of magnitude as the square root of the discriminant, but you have to take a log term to deal with the discrepancy. For constants C and C prime, independent of D. So in particular, it grows at a very standard rate, so there can only be a finite number of these that have class number 1, and only a finite number of them have class number 2, and then only a finite number have class number 3, etc. Because eventually this number becomes bigger than any integer. Okay? Now we haven't been able to prove this yet. This is still open. This part is known, that the class number is not too large, but this part is a big open problem. And I'm going to show you that it's rather closely related to another huge open problem in number theory called the Riemann hypothesis. It doesn't look like this should be so closely connected to the Riemann hypothesis, but it is. The Riemann hypothesis is one of the questions that this big donor to mathematics, Landon Clay, has offered $1 million if you can prove it. Of course, that would be the worst possible reason to attack a great problem in mathematics, right? But nonetheless, if you want to know, you can get $1 million. Probably if you could prove this, you'd get $1 million too. Yes?
Over here where you've written the proposition,
Yes.
that quotient group, that's within Q, not within R, right?
No. It's let's go slowly. The ideals form a group. The ideals of R, fractional ideals form a group. That's correct.
So what I want to get at is like,
Every class is represented by an actual ideal. Every class is represented by a real ideal, not just a fractional ideal. So not every element of this group is a genuine ideal. It's a fractional ideal. But if you allow yourself to modify it by a principal ideal, you can make it a genuine ideal. And the reason is this. That's a good question. Let me just say that very briefly. If you have a fractional ideal, then it has a basis. Again, it's one of these lattices. So it looks like Z alpha plus Z beta, where alpha and beta are in this field. Okay? Alpha and beta are numbers, so they have a fixed denominator. Some denominator. So since alpha and beta are in Q squared of D, there exists some integer n bigger than or equal to 1 with n alpha, n beta in R. Namely, these are algebraic numbers. They satisfy some polynomial with rational coefficients. Right? So by clearing denominators, by multiplying them by a large integer, you can make them satisfy a polynomial with integer coefficients. Therefore, an R are the things that satisfy polynomials with integer coefficients. Okay? So by multiplying them by a large integer, you can move them into R. And that implies that if you multiply the ideal I by the ideal nr, that's contained in R. Because n times this ideal I has basis n alpha and n beta. And so up to multiplication by principal ideals, everything can be moved into R. So every element of this class group is actually represented by a genuine ideal. Every coset of this subgroup is represented by a genuine ideal, not just a fractional ideal. That's why Peter's construction worked. If you compare his, why they're the same group. Did that answer your question? Okay. So it looks like you need fractional ideals, but if you're just talking about the quotient group, you could do it all with integral ideals, with genuine ideals. Okay? Okay. So the question is, why, first of all, is the class number approximately the square root of the discriminant? Why is it related to the Riemann hypothesis? And why does this become a problem that has almost nothing to do with algebra? It becomes a problem in analysis, in the theory of functions. That's a totally amazing thing. No one has really been able to show any of these estimates by just studying the rings. The rings all look the same. The rings have a class group, and the class group is finite, and that's all you can say. It's sort of hard to see why this ring has class number 1, and you go to the next discriminant, and the class number will be 7 or something. It's sort of completely random. But there's a nice analysis method to attack this problem, and I thought I'd end with that so that you could see that these areas of algebra and the areas of analysis, and if you're studying Math 113, complex analysis, all tie together. Okay, so let me try to give you the background at Gauss's estimate. This, by the way, this result right here, class number 1, that's Gauss's theorem that the Gaussian integers are a Euclidean domain. This is the thing that square root of 2 is a Euclidean domain. This is the statement that if you take this ring over here, it's a Euclidean domain. This is the statement down here that the square root of minus 5, z plus z squared of minus 5, is not a unique factorization domain, the fact that this is bigger than 1. Okay, so it contains all of our previous results, this business about class numbers. Okay, so now we go into the world of analysis. And this is, I think, one of the greatest discoveries of 19th century mathematics, that there were infinite series and functions that were related to the study of these rings. So I should tell you, first of all, there's a very famous infinite series that was introduced by Euler in the middle of the 18th century called the zeta function. And the zeta function was given by this sum. One over n to the s power. Or you could think of this as x, but it's better to think of it as s because, well, that's the classical notation, and you think of s as a complex variable or a real variable. But let's think of it as a real variable, and we better take it bigger than 1 so this series converges. Right? I mean, that's one thing we prove in calculus. The sum of 1 over n squared converges. The sum of 1 over n cubed converges. But the sum of 1 over n, that's the harmonic series that diverges. So Euler studied this function in the range of convergence, and he proved the following beautiful result about it, which is his restatement of the unicity of prime factorization. That it was given by a product over primes of 1 minus 1 over p to the s, these are prime numbers, inverse. That it was given by not only an infinite sum, but an infinite product. And the reason is the following. If I'm just waving my hands at this lecture, you're not going to hold me to convergence or anything like that. The reason is that if you expand this out, this is like a 1 minus x, 1 over 1 minus x looks like 1 plus x squared plus x cubed, right? So if you apply that to this series, you'd get 1 plus 1 over p to the s plus 1 over p to the 2s plus 1 over p to the 3s plus etc. That would be the individual term in here. It would be that infinite sum. And if you imagine multiplying all these sums together and using the fact that every integer has a unique prime factorization, see, if I multiplied this by the term 1 plus 1 over q to the s plus 1 over q to the 2s plus, where q is another prime, I multiplied this times this, what would I get? I get 1 plus 1 over p to the s plus 1 over q to the s plus 1 over pq to the s plus, right? Because here I'd have the 1 over p to the s, here I'd have the 1 over q to the s, and here I'd have the 1 over pq to the s. And if you multiply them out, you see you get all the numbers 1 over n to the s, where n only involves the prime factors p and q. But if I multiply all these things, I get all integers, because every integer appears with a unique prime factorization. And that was Euler's amazing observation. And he did an awful lot with this. For example, he gave a really good proof that there were infinitely many primes. Here's a proof that there are infinitely many primes from this. Okay? If there were finitely many primes, this would be a finite product. So it would converge for all values of s. Right? But this doesn't converge for s equal 1. So, I mean, that's like the first great proof of the infinitude of primes since Euclid. And then Euler did even better. He proved there were so many primes. A corollary of this, which I won't prove for you, he's proved that the sum of 1 over p is infinite. So that's pretty good. Okay? So that was Euler's result. And this was very famous and was well known to all the people who worked in number theory in the 19th century. Now, Last time Peter said that any ideal might not have a nice factor, every element might not have a unique factorization, but every ideal has a unique factorization into prime ideals. Right? That's the generalization of. Now, if you think about this, this sum from n equal 1 to infinity, these are the different indices of ideals of the integers. Every ideal of the integers has the form is a principal ideal generated by some n, and the index of this ideal is the absolute value of n, which is greater than or equal to 1, right? So that led Dirichlet in 1837, and this is, I say, one of the great breakthroughs of 19th century mathematics, to introduce the following series. He associated a similar series to the ring R. He associated, you sum over all ideals in R, which are non-zero, and instead of 1 over n to the s, you put 1 over the norm of the ideal to the s. Okay, this is the index, remember? And that's a positive number, so you can exponentiate it. And he proved that there weren't too many ideals, so that this series was also convergent when s was bigger than 1, just like it was in the integer case. So this is a function that Euler called the zeta function of s. So this Dirichlet called this the zeta function associated to the ring R of s. And associated to the ring, he had this analytic function of a variable. And the theorem that every ideal is a product of prime ideals, he said, well, that translates into Euler's result, that this is a product over prime ideals of 1 minus 1 over the norm of p to the s inverse. And that's because if you factor an ideal as the product of prime ideals uniquely, then it turns out that the norm of that ideal is the product of the norm of the prime ideals. That's not hard to show. So that this beautiful theorem that Euler had discovered on the zeta function factoring in as a product was also true for these rings, where instead of, you didn't put a number here, you put the sum over all ideals, the norm of the ideal, and then you factored into prime ideals. Okay, now, here was Dirichlet's second observation, which was just as brilliant as the first. We saw that the prime ideals, at least in the Gaussian integers, corresponded to rational primes. And a rational prime could behave in one of three ways. So if P is a rational prime, you have three possibilities. One, PR can be a prime ideal. So it remains prime. Two, there are two prime ideals between PR and R, each of index P, because this, with I should have said, the norm of PR equal P squared, because its index is P squared. Or this can have index P squared in R, but not be a prime ideal, not be maximal. There might be two ideals between it, such that P times P prime is equal to PR. And that's this case we found in the Gaussian numbers when P was congruent to 3 mod 4. And this case we found in the Gaussian numbers when P was congruent to 1 mod 4. And the final case, which only occurs finitely many times, is there is a single 1 prime ideal between PR and R with P squared equal PR. And this has index P. And that's the case we found in the Gaussian numbers when P was equal to 2. Okay? So when we take this product, we can rewrite it as a product over rational prime numbers. And this is what Dirichlet did. product over rational prime numbers, and you get 3 different cases. In the first case, you get 1 minus 1 over p to the 2s inverse. That's when there's a unique prime dividing r, and its norm is p squared. Or, in the second case, you'd get 1 minus 1 over p to the s inverse times 1 minus 1 over p to the s inverse. That's when they're 2 prime ideals, and they each have index p, so you get 2 contributions to this product. And the third case, you just get 1 contribution, and it looks like this. So according to how the rational prime behaves in the ring R, whether it remains prime, whether there are 2 ideals between it, whether there's 1 ideal, the factors that you get here you can group according to rational primes, and you get these factors. Okay, now look. Compare this product to this product, the original zeta function. Notice that this term here divides each of these terms. Right? Here it's just equal to the term. Here it's one of these terms. And here it divides it because I could write this thing as 1 minus 1 over p to the s inverse times 1 plus 1 over p to the s inverse. If you multiply those two, you get 1 minus 1 over p to the 2s inverse. So each case, I have this term that already appeared in the zeta function times a little bit more. Okay? And what Dirichlet proved was that this function of s divided this function of s, and what you were left with was the product over those primes. And he called that the quotient function. He called it L of s, which is zeta r of s as a function divided by zeta of s is given by an infinite product, p, of 1 plus or minus p to the minus s inverse for the rational primes p, where this plus or minus depends on how the prime behaves in the ring. Okay, now let's take a look and see what happens to that for the Gaussian numbers. Because there we've worked out everything, we can actually see what series we get. Well, for the Gaussian numbers, it would look like this. For z of I, it turns out that this L of s looks like this. The product over p congruent to 1 mod 4, those are the things with 2 factors of 1 minus 1 over p to the s inverse. And then the product over p congruent to 3 mod 4 of 1 plus 1 over p to the s inverse. And then you don't get anything for p equal 2 because there the term cancels exactly. Okay? Now let's do the Euler business of recombining these products into some sum like this. And you see that you're going to get, you have all the odd primes here. So when you product these things out, you're only going to get the odd numbers. If the numbers are congruent to 1 mod 4, they're going to appear with a plus sign. And if they're congruent to 3 mod 4, they're going to appear with a minus sign. So when you gather things up here, it looks like this. 1 minus 1 over 3 to the s, plus 1 over 5 to the s, minus 1 over 7 to the s, plus 1 over 9 to the s, minus 1 over 11 to the s, etc. Equals a sum over n greater than or equal to 1, odd, plus or minus 1 over n to the s. And the plus or minus depends on whether it's 1 mod 4 or 3 mod 4. So this quotient of the zeta function of r that measured how many ideals you have of given norm in r by the zeta function of the integers, which is this classical function, is this rather nice series here. And notice that even though this thing doesn't converge at s equal 1, and likewise this thing doesn't converge at s equal 1, because you can prove that, the quotient does converge at s equal 1. And in fact, this converges at s equal 1. L of 1 is 1 minus a third plus a fifth minus a seventh plus a ninth. Yeah, good. Is what Leibniz proved was pi over 4. Converges. So Dirichlet knew all that. I mean, he knew the mathematics of his time. And so he suspected that this series, this L of s, converged. Because you get things like 1 over n to the s, that's fine, but they come with plus and minus signs, so they don't add up like the harmonic series added up. See, these all come with plus signs. And likewise, in here they're all with plus signs. But once you take this product, you get, sum over, it turns out, n prime to the discriminant, n bigger than or equal to 1, plus or minus over 1 over n to the s. And there's enough cancellation so that Dirichlet proved that L of 1 exists, and he found a formula for it called the class number formula, which is his great achievement. And the class number formula of Dirichlet is a formula for L of 1. In terms of the ring, that it's equal to 2 pi over the square root of the absolute value of the discriminant times the class number of the ring divided by the number of units. Is that a great formula or what? So let's see what it says over here. It says that whatever this sum is, it's equal to 2 pi over the square root of the discriminant. That's the square root of 4, right? Because the discriminant is minus 4, times the class number of the Gaussian integers, which we assume we don't know yet, divided by the number of units, which is 4. Correct? 4 units in the Gaussian integers. And so you get pi over 4 times h. So by Dirichlet's formula, whatever this thing converges to, it converges to some integer multiple of pi over 4. Now, you can see immediately that that integer has to be 1, because it's an alternating series. So its limit is between the top term and the next term. Alternating series go back and forth like that, and then they converge. So it's less than 1 and bigger than 2/3. And the only multiple of pi over 4 that's less than 1 and bigger than 2/3 is 1 times pi over 4. So that's Dirichlet's proof that this is a principal ideal domain. But in general, you just get this formula for it. This number is almost always 2, right? The number of units we showed was 2 once the discriminant was not minus 3 or minus 4. So basically, what you have here is that the value of this function is 1, is some constant, pi, times the class number divided by the square root of the discriminant. And this, Dirichlet realized, was the reason that the class numbers were growing. Because what you want to conjecture, and this is what no one can prove, see, this number is clearly non-zero. These are all positive numbers. You want to show that the value of this function at 1 is not too small as a real number. Because if you could show if L of 1 is about the same size as the constant 1, namely it's not 10 to the minus 70th or something, but it's about the size of 1, then that shows that the class number is about the same size as the square root of the discriminant. Right? Which is, this is all just constants. So to show that this is large is to show that the class number is growing like the square of the discriminant. And that's how all approaches to this conjecture of Gauss's that I've just erased have gone. To try to attack this analytic function, which is analytic number theory, and to try to show that this number is not too small. Okay, now what is the relation of that with the Riemann hypothesis? The Riemann hypothesis says that this function here, the zeta function, Riemann conjectured that all zeros of zeta of s with the real part of the 0 between 0 and 1 have real part equal to a half. So I have to say what that actually means, because so far we've only defined this series for s greater than 1. It only converges when s is bigger than 1. Well, if you know complex function theory, that series will converge when the real part of s is bigger than 1, because the absolute value of 1 over n to the s is 1 over n to the real part of s. So as long as the real part of s is larger, if the real part of s is bigger than 1, then zeta of s converges absolutely. If you haven't taken Math 113, don't worry about it. And so to draw a picture of the complex plane, here's the point s equal 1. And in this area of the complex plane, we have a well-defined function. And what Riemann first proved was that there was a pole of that function at s equal 1. So Riemann proved that zeta of s minus 1 over s minus 1 has an analytic continuation to the entire plane. Namely, there's a well-defined function on the entire plane which is unique, which because of this would blow up at s equal 1, so that you can talk about the values of zeta function in the entire plane as long as you stay away from the point 1. And then he noticed that all the interesting behavior of the function was between this line and this line. That's called the critical strip of the zeta function. This is the point s equals 0. And he began to look for its zeros, and he found that the zeros were right in the middle of the strip. Namely, he located the first few zeros of the function, and they were always on the line s equal a half. And that's the main unsolved conjecture in pure mathematics, this question. Now, what does that say? Suppose that were also true for this other zeta function, the zeta function of r. And that seemed like a reasonable thing to Dirichlet to conjecture, that it should be also true for the zeta function of r. Namely, its zeros should be away from the point s equal 1. Then this number, then the L function, which is the quotient of these two things, should also have its zeros away from s equal 1. And as long as the zeros are away from s equal 1, then the value at s equal 1 can't be too small, because if it was very small, you'd have a zero rather close to s equal 1. That's more or less the relationship to the Riemann hypothesis. So this number is positive, but it can't be something like 10 to the minus 400th power, because if it were, then if you move just a little bit to the left of s equal 1, you'd have a 0, and that would contradict the zeta function, the Riemann hypothesis for this function. Anyhow, we're now in the realm of analytic number theory, and they have all kinds of tricks of their own. I hope you'll all go on to study it. This kind of formula is proved, I think. Now we give a nice course, Math 129, which is more advanced number theory, algebraic number fields, etc. And this kind of formula is proved. Believe me, it's totally cool. OK, so I'll just tell you how I got involved in this problem. So what happened was there was an analytic number theorist when I was in graduate school. He now teaches at Columbia, whose name is Dorian Goldfeld. And he took the following approach to this. It had been previously proved by the great analytic number theorist of the 20th century, Carl Ludwig Siegel, that if one of these things were small, if for one ring R this number were too small, then the class numbers were like this for all the other rings R. So Siegel proved if false for 1D, true for all others. Now that sounds like a great result, but you don't know which that 1D is. And probably it isn't false for that 1D. So you could never give, for example, a list of the things where the class number was 1, because there could have always been one more. So it was a rather unsatisfactory result, and Siegel used the fact that he had a zero of one of these functions that was rather close to 1 to push all the other zeros away. So Goldfeld had this wonderful idea, and he said, look, Siegel's zero doesn't really exist anyhow. But I do know how to make other functions like this with products and everything. So you make another function, another series, related to an elliptic curve, with a high order 0, at s equal 1. And from the theory of elliptic curves, we believed we'd have such functions. And he used that high order 0 for an elliptic curve to show that these things could not be too small. That was the technique in analytic number theory. And everyone thought, oh, this is great, we've solved the problem. And then people realized, wait a minute, we don't really know how to make these series with a high order 0. We just know how to make them where we compute them, and they appear to have a high order 0. So we made all kinds of infinite series with elliptic curves, and you'd compute like this. You'd compute L of 1 is equal to 0.0000000, 40 places. And then you'd compute L prime of 1 is 0.00000, 40 places. And then you'd compute the second derivative at 1, and it would be 0.00040 places. And you'd say, well, you know, that looks like it has a third order 0 at least, right? But you can't ever prove that an analytic function vanishes on the computer, if you think about it. There's no way to prove a function vanishes, because it could be, the value at 1 could have been this. Right? You should have just computed another place. You can't tell 0 apart from another number on a computer. In any epsilon neighborhood of 0, there are billions and billions and billions of stars. Right? So we realized, after Goldfeld had come up with this, that we actually had to make an elliptic curve where we could prove a high order 0. And to prove a high order 0, we had to prove exact formulas for these L functions analogous to this. More complicated, but analogous to this. See, this number, I know it's positive because it's some constant times an integer. I mean, I really know what this thing is. I have an algebraic interpretation of it in terms of the class group and the unit group and everything. So what I was able to do is prove a formula for the L function of elliptic curves that guaranteed that the first 3 derivatives, the value of the first derivative and the second derivative, were 0 in certain cases. And that allowed one to plug into Goldfeld's method. And although one doesn't know now that the class number is about the size of the square root of the discriminant, we were able to prove the class number was bigger than the constant times the log of the discriminant, which is a horrible, horrible estimate. But it's enough to show that it goes to infinity. I don't think this is the real point of what I did, but it was a corollary of it. And the real point was to come up with formulas like Dirichlet's for the L functions of elliptic curves. So you'll also want to learn about those too. Those of you who took Williams' seminar last year know about the Burchard, Swinnerton, Dyer conjecture. It's another way you can make $1 million. So I look forward to seeing you all in January. Have a great vacation. Work on the Riemann hypothesis. Work on learning about rings. And I'll see you back then. Have a good time.